So please go back to the notes. So phi star itself is not does not have the correct transformation property under SU2 transformation, but phi c does, and that is what comes here. And L, similar to the quark doublet, there is a leptonic doublet, which is the neutrino, left-hander neutrino, and the left-hander electron field. So these are the two doublets, and in the leptonic sector, ER is a singlet, and nu R is banished. Nu R not present in the standard model. Let me simply say banished. Do you know why? Because nu R does not have any SU2 cross U1 interactions. Because it is a singlet, it does not have SU2 interaction, and since you will see the hypercharge also is 0, I am going to prove that. So because of that, it does not have any gauge interaction, so it has been removed from standard model, the original standard model. The standard model has to be modified if nu R has to be brought in, and that I am not discussing now. Okay. And UR and DR are singlets, I already mentioned it. So now this phi c, if you write phi itself, we will write as doublet, phi 1, phi 2 we will write, but instead I will put the charges. They have charges also, phi plus, phi 0, whereas this phi c will have phi 0 bar and minus phi minus. It is this minus which comes from this minus. Okay. Now everything is defined. Now we have got an SU2 cross U1 theory. So not only under SU2 it should be invariant, it is clear that under SU2 it is invariant. How? QL bar phi, if you take some doublet and another doublet, spin half, isospin half plus isospin half can give you isospin 0. The way to form is one of them should be starred or bar, anything like that. Then you can see that this is a column vector, this is a row vector, and so it is matrix multiplication is involved, so that this becomes a number. So this is invariant, SU2 invariant. Similarly, here this is also invariant. Similarly, this is invariant, and this is singlet. So in invariant multiplied by a singlet remains invariant. So every term is SU2 invariant. What about U1? Because it's an SU2 cross U1 theory. So U1 invariance. U1 invariance also, the generator of U1 we call hypercharge. Again, I say I am using isospin language here, so I am using the old strong interaction language, hypercharge. And remember the Gell-Mann-Nishijima formula, charge is equal to the third component of isospin plus, I think I had defined it as y by 2, but now I am going to define it as just y. That is the way hypercharge. Namely, the generator of the U1 transformation in the SU2 cross U1 theory has to be obtained like this, because this is what will fix. So must be invariant under SU2 cross U1. Sometimes this U1 it is called U1y and this is called SU2L because it is left-handed. This is U1 hypercharge, because there is one U1 electromagnetism. Remember last time when I worked out the Higgs mechanism for the SU2 cross U1, the electromagnetism remained intact, and so correspondingly there is a U1, that is U1Q, Q being the electric charge, but this is U1y, and they are displaced by the I3 factor. Okay, must be invariant. So we are going to check this. So we have to work out y. So I called this Yukawa. Why? Because remember what this does. This says one fermion becomes another fermion by emitting a scalar boson. This type of coupling, fermion-fermion scalar coupling, are called Yukawa couplings, because it was Yukawa in 1930 3 or so, first he introduced the interaction of the nucleon with the pion. Remember, that was the original breakthrough in understanding pion. And so in honor of that, Yukawa was given Nobel Prize. So any such term, a fermion scalar term, is called Yukawa coupling. That is why it's called Yukawa. Yukawa. Now hypercharge, let us work out the hypercharge for a few particles, QL, LL. For the doublets, both the upper and lower components should have the same hypercharge. That is why when I3 changes, correspondingly Q will change. And then the singlets UR, DR, and ER, leptons, and nu are also, let us write down for the time being, and then the phi. Please work these out. You will find that the Y quantum numbers are, here it is 1/6, because we know a charge for the Q which is equal to plus 2/3. Remember that plus 2/3. I3 is plus half, it's upper component. So subtracting that, you will get 1/6. For the quarks, they are always fractions of that kind. For LL, similarly, it will be minus half, because let us take neutrino. Neutrino has charge 0 and I3 equal to plus half. So to cancel that, minus half. And U are plus 2/3 and I3 is 0, so this will be 2/3 only. Similarly, DR will be minus 1/3. For these, the hypercharge is the same as the electric charge. For ER, again put minus 1, you will get here minus 1. And for nu R, it will be 0. Because electric charge is 0 and I3 also is 0 because right-handed. So the left-handed, this I is left-handed I, remember, left-handed SU2. And for phi, again substitute, I have already given the charge assignment, just put it, you will find it is equal to plus half. So that is the table of hypercharges, which is what will complete our discussion. Now this is very important because this should be invariant not only under SU2 but invariant under U1. Invariance under U1 can also be regarded as conservation of the hypercharge. Why? You can see by by these hypercharges, this will have hypercharge conservation. Or you add the hypercharges, hypercharge will become 0 here. QL bar is minus 1/6 and phi is plus half and DR is minus 1/3. Add all of them, it will be 0, hypercharge will be 0. So just check. And that is the reason why I cannot put phi itself here. This is phi, and for phi c it is naturally phi c, it is minus half. If you put phi here, hypercharge will not be 0. That is why I have to bring in phi c. And similarly here also you can check the hypercharge is 0. If nu r is brought in, then that will have like phi c, because nu r behaves like ur, whereas er behaves like dr. Okay, now it is this Yukawa term after spontaneous symmetry breaking generates masses. How does it do it? It's very simple to understand it now. So in the Yukawa part of the Lagrangian, Yukawa, which I have written down, replace all the phi's by their vacuum expectation values. So, this gives you here Yukawa replacing by vacuum expectation values. Replace phi and phi c by their vacuum expectation values. So, this will become minus Hd. Let me write it down explicitly. QL bar is remember UL bar DL bar. The row will become, column will become row, and phi will become remember vacuum expectation value cannot exist for phi plus. So, that is because phi plus is charged, and if there is vacuum expectation value, charge conservation will go what. So, only this phi 0 picks up a non-zero vacuum expectation value, and remember we called it rho, I think. After taking out the phase, this becomes a rho, and so this is the one has vacuum expectation value phi 0 vacuum expectation value. So, let us write it down as 0 phi 0 vacuum expectation value, and then dr. Similarly, HU UL bar DL bar. Now, the vacuum expectation value is for this. So, it is the upper component, and phi 0 the vacuum expectation value is real. So, phi 0 bar and phi 0 vacuum expectation values are the same. So, this is phi 0 vacuum expectation value 0 into UR. Then HE nu L bar E L bar 0 phi 0 vacuum expectation value into ER, that is all, plus Hermitian component. So, if you do these matrix multiplications, you get minus HD DL bar into DR will come. So, phi 0 will come. So, let me write phi 0 here into DL bar DR plus HU phi 0 UL bar UR plus HE phi 0 EL bar ER plus Hermitian conjugate. So, that is it. And what is the Hermitian, because Hermitian conjugate is needed. So, let me work it out. DL bar DR Hermitian conjugate will be DR, because it will get order will get reversed, and remember there is a gamma 0 here. So, gamma 0 dagger will be gamma 0, otherwise it is DL, that is all, which can be written as DR bar DL. So, Hermitian conjugate of DL bar DR is nothing but DR bar DL, and similarly for those. So, and remember, let me first write it down, minus HD DL bar DR plus its Hermitian conjugate DR bar DL. Similarly, for the other terms, HU UL bar UR plus UR bar UL plus HE into EL bar ER plus ER bar EL. So, we have added the, and remember this is nothing but d bar d. I already showed you last time d, when you write d as dl plus dr, you will have 4 terms, but the dl bar dl and dr bar dr are 0 because of the properties of gamma phi, 1 plus gamma phi into 1 minus gamma phi. So, only the cross terms survived, I think I told you earlier. So, this is nothing but dr d, and this is u bar u, and this is u bar e. So, these are the mass terms, because I think I forgot something. HD, there is a let us write phi 0 is common anyway. Phi 0 I wrote above. Okay. Phi 0 vacuum expectation value. Therefore, the mass of the d quark is really the Yukawa coupling times the vacuum expectation value. Similarly, for mu and the electron mass. So, we have generated the mass terms by spontaneous breakdown of symmetry. It is a non-zero Higgs vacuum expectation value which gives, and the mass of the fermion is nothing but vacuum expectation value times the Yukawa coupling. And m nu is 0 because we did not have nu r. Since nu r is banished, m nu is 0. Now, the fermions of the other generations also can add. Remember, this is only the first generation UD. We have to take CS and TB. Similarly, for leptons, neutrino electron, neutrino muon, and neutrino tau. But those can be treated exactly in the same manner. But there is one non-trivial feature which is coming up. Maybe that I will discuss after the break. When you add the other generation, there is one non-trivial factor which is coming. Okay. If there is any question, you can ask me now.
What did you say about neutrino at the end?
Since I had banished nu r, since it did not have the SU2 cross U1 gauge interactions, since it was a singlet under
that is why.
because since nu r does not exist, you cannot generate mass for the neutrino even with the Higgs mechanism.
Okay.
Okay.
Yeah.
So we will join after a while. I will come back by 11:15. You can ask questions at that time.
Yeah.
give a possibility.